Our discussion for today in our session is all about matrix analysis of structure, and to start with, we have its introductory concepts. And to introduce myself, I am Professor Danilo M. Guzman Jr., a registered civil engineer, a registered master plumber, licensed professional teacher, and a graduate of MAHED, Master of Arts in Education, major in mathematics. Let us now start our discussion. Let us now start the discussion regarding about our introductory concepts. Structural analysis, which is an integral part of any structural engineering project, is the process of predicting the performance of a given structure under a prescribed loading condition. The performance characteristics usually of interest in structural design are the following. First, we have the stresses or stress resultants. In example, axial forces, shears, and bending moments. Then followed by deflections and also support reactions. Thus, the analysis of structure typically involves the determination of these quantities such as caused by the given loads and or other external effects such as support, displacement, and temperature changes. Many commonly used structures such as beams and plane and space trusses and rigid frames are classified as frame structures, also referred to as skeletal structures. In most design offices today, the analysis of frame structures is routinely performed on computers using software based on the matrix methods of structural analysis. It is therefore essential that structural engineers understand the basic principle of matrix analysis so that they can develop their own computer programs and or properly use commercially available software and appreciate the physical significance of analytical results. The objective of this text is to present the theory and computer implementation of matrix methods for the analysis of frame structures in static equilibrium. Let us now have a historical background of the matrix analysis of structure. The theoretical foundation for matrix methods of structural analysis was laid by James Maxwell, who introduced the method of consistent deformations in 1864, and George Money, who developed the slope deflection method in 1915. These classical methods are considered to be the precursors of the matrix flexibility and stiffness methods, respectively. In the pre-computer era, the main disadvantage of these earlier methods was that they required direct solution of simultaneous algebraic equations, a formidable task by hand calculations in cases of more than a few unknowns. The invention of computers in the late 1940s revolutionized structural analysis, as computers could solve large systems of simultaneous equations. The analysis methods yielding solutions in that form were no longer at a disadvantage, but in fact were preferred because simultaneous equations could be expressed in matrix form and conveniently programmed for solutions on computers. Mr. Levy is generally considered to have been the first to introduce the flexibility method in 1947 by generalizing the classical method of consistent deformations. Among the subsequent researchers who extended the flexibility method and expressed it in matrix form in the early 1950s were Falkenheimer, Landsfors, and Denke. The matrix stiffness method was developed by Livesley in 1954. In the same year, Argyris Kelsey presented a formulation presented a formulation of matrix methods based on energy principles. In 1956, Turner, Clough, Martin, Top derived stiffness matrices for the members of classes and frames using the finite element approach, and introduced the now popular direct stiffness method for generating the structure stiffness matrix. In the same year, Lipsley presented a nonlinear formulation of the stiffness method for stability analysis of frames. Since the middle of 1950s, the development of matrix methods has continued at a tremendous pace, with research efforts in recent years directed mainly toward formulating procedures for the dynamic and nonlinear analysis of structures, and developing efficient computational techniques for analyzing large structures. Recent advances in these areas can be attributed to Mr. Archer, Bernstein, Gallagher, Padlog, Zemyansky, Wang, Wilson, and among others. We now have the classical, matrix, and finite element methods of structural analysis. And to start with, let us have first the classical versus matrix methods. As we develop matrix methods in subsequent chapters of the subject, learners who are familiar with classical methods of structural analysis will realize that both matrix and classical methods are based on the same fundamental principles, but that the fundamental relationships of equilibrium, compatibility, and member stiffness are now expressed in the form of matrix equations, so that the numerical computations can be efficiently performed on a computer. More classical methods were developed to analyze particular types of structures, and since they were intended for calculations, they often involve certain assumptions to reduce the amount of computational effort required for analysis. The application of these methods usually requires an understanding on the part of the analyst of the structural behavior. Consider, for example, the moment distribution method. This classical method can be used to analyze only beams and plane frames undergoing bending deformations. Deformations due to axial forces in the frames are ignored to reduce the number of independent joint translations. While this assumption significantly reduces the computational effort, it complicates the analysis by requiring the analyst to draw a deflected shape of the frame corresponding to its degree of freedom of sideway. To estimate the relative magnitudes of member, peaks, and moments, a difficult task even in the case of a few degrees of freedoms of sideway, if the frame has inclined members because of their specialized and intricate nature. Classical methods are generally not considered suitable for computer programming. In contrast to classical methods, matrix methods were specifically developed for computer implementation. They are systematic and general. It will become clear as we study matrix methods that because of the latter characteristic, a computer program developed to analyze one type of structure can be modified with relative ease to analyze another type of structure, an example, space trusses or frames. As the analysis of large and highly redundant structures by classical methods can be quite time consuming, matrix methods are commonly used. However, classical methods are still preferred by many engineers for analyzing smaller structures because they provide a better insight into the behavior of structures. Classical methods may also be used for preliminary designs for checking the results of computerized analysis and for deriving the member force displacement relations needed in the matrix analysis. Furthermore, A study of classical method is considered to be essential for developing an understanding of structural behavior. Let us have now the matrix versus finite element methods. Matrix methods can be used to analyze frame structures only. Finite elements analysis, which originated as an extension of matrix analysis to surface structures, has now developed to the extent that it can be applied to structures and solids of practically any shape or form. From a theoretical viewpoint, the basic difference between the two is that in matrix methods, the member force displacement relationships are based on the exact solutions of the underlying differential equations, whereas in finite element methods, such relations are generally derived by work energy principles from assumed displacement or stress functions. Because of the approximate nature of its force displacement relations, finite element analysis generally yields approximate results. However, as will be shown in Chapter 3 of this subject matter, or of this subject, and 5, in the case of linear analysis of frame structures composed of prismatic uniform members, both matrix and finite element approaches yield identical results. Let us have a discussion now about flexibility and stiffness methods. Two different methods can be used for the matrix analysis of structures: the flexibility method and the stiffness method. The flexibility method, which is also referred to as the first or compatibility method, is essentially a generalization in matrix form of the classical method of consistent deformations. In this approach, the primary unknowns are the redundant forces, which are calculated first by solving the structure's compatibility equations. Once the redundant forces are known, the displacement can be evaluated by applying the equations of equilibrium and the appropriate member force displacement relations. The stiffness method, which originated from the classical slope deflection method, is also called the displacement or equilibrium method. In this approach, the primary unknowns are the joint displacement, which are determined first by solving the structure's equations of equilibrium. With the joint displacements known, the unknown forces are obtained through compatibility considerations and the member force displacement relations. Although either method can be used to analyze frame structures, the flexibility method is generally convenient for analyzing small structures with a few redundants. This method may also be used to establish member force displacement relations needed to develop the stiffness method. The stiffness method is more systematic and can be implemented more easily on computers. Therefore, it is prepared for the analysis of large and highly redundant structures. Most of the commercially available software for structural analysis is based on the stiffness method. In this text, we focus our attention mainly on the stiffness method, with emphasis on a particular version known as the direct stiffness method, which is currently used in professional practice. We have now the classification of frame structures. Frame structures are composed of straight members whose lengths are significantly larger than their cross-sectional dimensions. Common frame structures can be classified into six basic categories based on the arrangement of their members and the types of primary stresses that may develop in their members under major design loads. At first, we have the plane trusses, followed by the beams, and then we also have the plane frames, followed by the space trusses, and then we also have the grids, and lastly, we have the space frames. Let's now have the definition of plane trusses. A truss is defined as an assemblage of straight members connected at their ends by flexible connections and subjected to loads and reactions only at the joints or connections. The member of such an ideal truss develop only axial forces when the truss is loaded. In real trusses, such as those commonly used for supporting roofs and bridges, the members are connected by bolted or welded connections that are not perfectly flexible, and the dead weights of the members are distributed along their lengths. Because of these and other deviations from idealized conditions, truss members are subjected to some bending and shear. However, in most trusses, these secondary bending moments and shear are small in comparison to the primary axial forces, and are usually not considered in their designs. If large bending moments and shears are anticipated, then the truss should be treated as a rigid frame for analysis and design. If all the members of a truss as well as the applied loads lie in a single plane, the truss is classified as a plane truss. And as shown below, Figure 1.1 is an example of a plane truss. The members of plane trusses are assumed to be connected by frictionless hinges. The analysis of plane trusses is considerably simpler than the analysis of space trusses. Fortunately, many commonly used trusses, such as bridge and roof trusses, can be treated as plane trusses for analysis. And as shown below is an example of a roof truss. Of course, we also have beams. A beam is defined as a long straight structure that is loaded perpendicular to its longitudinal axis. Loads are usually applied in a plane of symmetry of the beam's cross-section, causing its members to be subjected only to bending moments and shear forces. And as shown below, Figure 1.3 is an example of a beam. Let's now have the definition of plane frames. Frames, also referred to as rigid frames, are composed of straight members connected by rigid and or flexible connections as shown in Figure 1.14 below. Unlike trusses, which are subjected to external loads only at the joints, loads on frames may be applied on the joints as well as on the members. As shown below is Figure 1.4. This is an example of a frame. If all the members of a frame and the applied loads lie in a single plane, the frame is called a plane frame. The members of a plane frame are in general subjected to bending moments, shears, and axial forces under the action of external loads. Many actual three-dimensional building frames can be subdivided into plane frames for analysis. And as shown below is the Figure 1.5. We have an example of a plane frame. Shown in Figure 1.6, this is an example of a segment of the integrated truss structure which forms the backbone of the International Space Station. And as shown below is an example of a grid which is actually our Figure 1.7. And now let us have a talk about the grids. Now, how do we define grids? A grid, like a plane frame, is composed of straight members connected together by rigid and or flexible connections to form a plane framework. The main difference between the two types of structures is that plane frames are loaded in the plane of the structure, whereas the loads on grids are applied in the direction perpendicular to the structure's plane. As shown in the figure, is an example of a figure of National Air and Space Museum located at Washington, D.C. Members of grids may, therefore, be subjected to torsional moments in addition to the bending moments and corresponding shears that cause the members to be bent out of the plane of the structure. Grids are commonly used for supporting roofs, covering large column-free areas in such structures as sports arena, auditoriums, and aircraft hangars. As shown in the figure, we have an example of a figure of a space frame. And now, how do we define space frames? Space frames constitute the most general category of frame structures. Members of space frames may be arranged in any arbitrary directions and connected by rigid and or flexible connections. Loads in any directions may be applied on members as well as on joints. The members of a space frame may in general be subjected to bending moments about both principal axes, shears in both principal directions, torsional moments, and axial forces. Let us now have a talk about analytical models. The first, and perhaps most important, step in the analysis of structure is to develop its analytical model. An analytical model is an idealized representation of a real structure for the purpose of analysis. Its objective is to simplify the analysis of a complicated structure by discarding much of the detail about connections, members, etc., that is likely to have little effect on the structure's behavioral characteristics of interest, while representing as accurately as practically possible the desired characteristics. It is important to note that the structural response predicted from an analysis is valid only to the extent that the analytical model represents the actual structure. For frame structures, the establishment of analytical models generally involves consideration of issues such as whether the actual three-dimensional structure can be subdivided into plane structures for the analysis, and whether to idealize the actual bolted or welded connection as ins, rigid, or semi-rigid joints. Thus, the development of accurate analytical models requires not only a thorough understanding of structural behavior and methods of analysis, but also experience and knowledge of design and construction practices. In matrix methods of analysis, a structure is modeled as an assemblage of straight members connected at their ends to joints. A member is defined as part of the structure for which the member force displacement relationships to be used in the analysis are valid. The member force displacement relationships for the various types of frame structures will be derived in subsequent chapters. A joint is defined as a structural part of infinitesimal size to which the ends of the members are connected. In finite element terminology, the members and joints of structures are generally referred to as elements and nodes respectively. Supports for frame structures are commonly idealized as fixed supports, which do not allow any displacement, in supports which allow rotation but prevent translation, or roller or link supports which prevent translation in only one direction. Other types of restraints, such as those which prevent rotation but permit translation in one or more directions, can also be considered in an analysis, as discussed in subsequent chapter. As shown below is an example of a figure of a plane truss. And then for the second one, we have a figure of analytical model example. With this, let us now talk about the line diagrams. The analytical model of a structure is represented by a line diagram, on which each member is depicted by a line coinciding with its centroidal axis. The member dimensions and the size of connections are not shown. Rigid joints are usually represented by points, and hinge joints by small circles at the intersections of members. Each joint and member of the structure is identified by a number. For example, the analytical model of the plane truss of figure 1.10a is shown in figure 1.10b, in which the joint numbers are enclosed within circles to distinguish them from the member numbers enclosed within rectangles. Let us now have the fundamental relationships for structural analysis. Structural analysis in general involves the use of three types of relationships. At first, we have the equilibrium equations. Second one, we have the compatibility conditions. And then for the last one, finally, we have the constitutive relations. For the first one that we have our equilibrium equations. Structure is considered to be in equilibrium if, initially at rest, it remains at rest when subjected to a system of forces and couples. If a structure is in equilibrium, then all of its members and joints must also be in equilibrium. As a recall from statics that for a plane, two-dimensional, structure lying in the x and y plane, and subjected to a coplanar system of forces and couples, as we can see at figure 1.11, the necessary and sufficient conditions for equilibrium can be expressed in a Cartesian xy coordinates as shown below. We now have this summation of forces horizontal or summation fx equals 0, summation of all forces vertical or summation fy equals 0, and the summation of all the moment equals 0 or summation m equals 0. These equations are referred to as the equations of equilibrium for plane structures. For a space, three-dimensional structure, subjected to a general three-dimensional system of forces and couples as shown in figure 1.12, the equations of equilibrium are expressed as summation fx equals 0, summation fy equals 0, summation fz equals 0, summation fx equals 0, summation my equals 0, and summation mz equals 0. For a structure subjected to static loading, the equilibrium conditions must be satisfied for the entire structure as well as for each of its members and joints. In structural analysis, equations of equilibrium are used to relate the forces acting on the structure or one of its members or joints. As we can see below, this is our figure 1.11. On the other hand, we also have our figure 1.12. For the second one, we have the compatibility conditions. Compatibility conditions relate the deformations of structures so that its various parts fit together without any gaps or overlaps. This condition ensures that the deformed shape of the structure is continuous and is consistent with the support conditions. Consider, for example, the two-member plane frame shown in figure 1.13. The deformed shape of the frame due to an arbitrary loading is also depicted using an exaggerated scale. When analyzing a structure, the compatibility conditions are used to relate member N displacement to joint displacement, which in turn are related to the support conditions. For example, again, because joint 1 of the frame in figure 1.13 is attached to a roller support that cannot translate in the vertical direction, the vertical displacement of this joint must be zero. Similarly, because the joint 3 is attached to a fixed support that can neither rotate nor translate in any direction, the rotation and the horizontal and vertical displacement of joint 3 must be equal to zero. The displacement of the ends of members are related to the joint displacement by the compatibility requirement that the displacement of members N must be the same as the displacement of joint to which the member N is connected. Thus, as shown in figure 1.13, because joint 1 of the example plane displaces to the right by a distance d sub 1 and rotates clockwise by an angle theta 1, the left end of the horizontal member 1, that is attached to joint 1 must also translate to the right by distance d sub 1 and rotate clockwise by angle theta 1. Similarly, because the displacement of joint 2 consists of the translations d sub 2 to the right and d sub 3 downward and the counterclockwise rotation theta 2. The right end of the horizontal member and the top end of the vertical member that are connected to joint 2 must also undergo the same displacement. The bottom end and the vertical member, however, is not subjected to any displacement because joint 3, to which this particular member end is attached, can neither rotate nor translate in any direction. Let's now have a view of our figure 1.13. Finally, compatibility requires that the deflected shapes of the members of a structure be continuous except at any internal hinges or rollers and be consistent with the displacement at the corresponding ends of the members. For the third one, we have the constitutive relations. The constitutive relations, also referred to as the stress-strain relations, describe the relationships between the stresses and strains of a structure in accordance with the stress-strain properties of the structural material. As discussed previously, the equilibrium equations provide relationships between the forces, whereas the compatibility conditions involve only deformations. The constitutive relations provide a link between the equilibrium equations and compatibility conditions that is necessary to establish the load deformation relationships for a structure or a member. In the analysis of frame structures, the basic stress-strain relations are precious, along with the member equilibrium and compatibility equations to establish relationships between the forces and displacement at the ends of a member. The member force displacement relations thus obtained are then treated as the constitutive relations for the entire structure and are used to link the structure's equilibrium and compatibility equations, thereby yielding the load deformation relationships for the entire structure. These load deformation relations can be then solved to determine the deformations of the structure due to given loading. The matrix methods presented in this text are formulated by the direct application of the equilibrium, compatibility, and constitutive relationships. However, to introduce readers to the finite element method and to familiarize them with the application of the work energy principles, we also derive the member force displacement relations for plane structures by a finite element approach that involves a work energy principle known as the principle of virtual work. In the following paragraphs, we review two statements of this principle pertaining to rigid bodies and deformable bodies for future reference. Let's now have the virtual work for rigid bodies, or the principle of virtual work for rigid bodies. The principle of virtual work for rigid bodies, also known as the principle of virtual displacement for rigid bodies, can be stated as follows. If a rigid body which is in equilibrium under a system of forces is subjected to any small virtual rigid body displacement, the virtual work done by the external forces is zero. In the foregoing statement, the term virtual simply means imaginary, not real. Consider, for example, the cantilever beam shown in Figure 1.14a. The free body diagram of the beam is shown in Figure 1.14b, in which Px and Py are the components of the external load P in the x and y direction respectively, and R1, R2, and R3 represents the reactions at the peak support 1. Note that the beam is in equilibrium under the action of the forces Px, Py, R1, and R2, and the couple R3. Now, imagine that the beam is given an arbitrarily small virtual rigid body displacement from its initial equilibrium position 1-2 to another position 1-2, as shown in Figure 1.14c. As this figure indicates, the total virtual displacement of the beam can be decomposed into rigid bodies. It can be decomposed into rigid body translations in the x and y direction respectively, and a rigid body rotation about point 1. Note that symbol like this is used here to identify the virtual quantities. As the beam undergoes the virtual displacement from position 1-2 to position 1-2, the forces and the couple acting on it perform work, which is referred to as the virtual work. The total virtual work can be expressed as the algebraic sum of the virtual work Wx and Wy performed during translations in the x and y directions, respectively, and the virtual work Wr done during the rotation, that is, equation 1.3 as shown below. The following that we have now, we have the figure 1.14 letter A and letter B. During the virtual translation of the beam, the virtual work performed by the forces can be expressed as shown below 1.4. Similarly, the virtual work done during the virtual translation is given by the formula shown below, equation 1.5. And the virtual work done by the forces and the couple during the small virtual rotation can be expressed as shown below, equation 1.6. The expression for the total virtual work can be now obtained by substituting equation 1.4 and 1.6 into equation 1.3. Thus, we have now the equation below 1.7. However, because the beam is in equilibrium, Fx equals 0, Fy equals 0, M sub 1 equals 0, therefore equation 1.7 becomes this as shown below, equation 1.8, which is actually the mathematical statement of the principle of virtual work for rigid bodies. Now let us have the principle of virtual work for deformable bodies. The principle of virtual work for deformable bodies, also known as the principle of virtual displacement for deformable bodies, can be stated as follows. If a deformable structure which is in equilibrium under a system of forces and couples is subjected to any virtual displacement consistent with the support and continuity conditions of the structure, then the virtual external work done by the real external forces acting to the virtual external displacement is equal to the virtual strain energy stored in the structure. To demonstrate the validity of this principle, consider the two-member truss as shown in Figure 1.15a, which is in equilibrium under the action of an external load P. The free body diagram of joint 3 of the truss is shown in Figure 1.15b. Since joint 3 is in equilibrium, the external and internal forces acting on it must satisfy the following two equations of equilibrium. First, we have the summation fx equal to 0, wherein negative f sub 1 sine theta 1 plus f sub 2 sine theta 2 is equal to 0, followed by the second one, the summation forces vertical equals 0, or summation fy equals 0, f1 cosine theta 1 plus f2 cosine theta 2 minus p is equal to 0, in which f1 and f2 denote the internal axial forces in members 1 and 2, respectively, and theta 1 and theta 2 are, respectively, the angles of inclination of these members with respect to the vertical, as shown in the figure. As shown below, we have our figure 1.15, letter A and letter B. As mentioned in here, that now we have to imagine that joint 3 is given a small virtual compatible displacement in the downward direction as shown in figure 1.15 letter A. It should be noted that this virtual displacement is consistent with the support conditions of the truss in the sense that joint 1 and 2, which are attached to supports, are not displaced. Because the reaction forces at joint 1 and 2 do not perform any work, the total virtual work for the truss is equal to the algebraic sum of the virtual work of the forces acting at joint 3. That's from figure 1.15 letter B. Well, and then, as shown in the picture, we have the summary of our two equations, equation 1.10 and equation 1.11, in which the quantity on the left-hand side represents the virtual external work performed by the real external force P acting through the virtual external displacement. Furthermore, because the terms are equal to the virtual internal displacement elongations of member 1 and 2, respectively, we can conclude that the right-hand side of equation 1.11 represents the virtual internal work done by the real internal forces acting through the corresponding virtual internal displacement, and that is, as shown below, we actually have the summary of two equations. We have equation 1.12 and equation 1.13. For computational purposes, it is usually convenient to express equation 1.13 in terms of the stresses and strains in the members of the structure. For that purpose, let us consider a differential element of a member of an arbitrary structure subjected to a general loading as shown in figure 1.16. The element is in equilibrium under a general three-dimensional stress condition due to the real forces acting on the structure. Now, as the structure is subjected to a virtual displacement, virtual strains develop in the element and the internal forces due to the real stresses perform virtual internal work as they move through the internal displacement caused by the virtual strains. For example, the virtual internal work done by the real force due to the stress as it moves through the virtual displacement caused by the virtual strain can be determined as follows. And now, let us have the following formulas, wherein Real force is equal to the product of stress and area, while virtual displacement is equal to strain times the length. Therefore, as we can see now, we have the virtual internal work formula, real force times virtual displacement, and followed by the virtual internal work in element dB, as shown in equation 1.14. And also we have the total virtual internal work or the virtual strain energy stored in the entire structure, which can be obtained by integrating equation 1.14 over the volume B of the structure. Thus, we have now this equation, and it is known as equation 1.15. Finally, by substituting equation 1.15 into equation 1.13, we obtain the statement of the principle of virtual work for deformable bodies in terms of the stresses and strain of the structure. You can see now the equation 1.16 as shown below. And now, let us have a talk about linear versus nonlinear analysis. In this text, we focus our attention mainly on linear analysis of structures. Linear analysis of structures is based on the following two fundamental assumptions. Number one, the structures are composed of linearly elastic material, that is, the stress-strain relationship for the structural material follows Hooke's law. Second one, the deformations of the structures are so small that the squares and higher powers of member slopes, rotations, and axial strains are negligible in comparison with the unity, and the equations of equilibrium can be based on the unreformed geometry on the structure. The reason for making this assumption is to obtain linear relationships between applied loads and the resulting structural deformations. An important advantage of linear force deformation relations is that the principle of superposition can be used in the analysis. This principle states essentially that the combined effect of several loads acting simultaneously on a structure equals the algebraic sum of the effects of each load acting individually on a structure. Engineering structures are usually designed so that under service loads, they undergo small deformations with stresses within the initial linear portions of the stress-strain curves of their materials. Thus, linear analysis generally proves adequate for predicting the performance of most common types of structures under service loading conditions. However, at higher load levels, the accuracy of linear analysis generally deteriorates as the deformations of the structure increase and or its material is strained beyond the yield point. Because of its inherent limitations, linear analysis cannot be used to predict the ultimate load capacities and instability characteristics, in example, buckling loads of structures. With the recent introduction of design specifications based on the ultimate strengths of structures, the use of nonlinear analysis in structural design is increasing. In a nonlinear analysis, the restrictions of linear analysis are removed by formulating the equations of equilibrium on the deformed geometry of the structure that is not known in advance, and or taking into account the effects of inelasticity of the structural material. The load deformation relationships thus obtained for the structure are nonlinear and are usually solved using iterative techniques. And for the summary of our entire discussion in this chapter 1, these are the following. Structural analysis is the prediction of the performance of a given structure under prescribed loads and or other external effects. Both matrix and classical methods of structural analysis are based on the same fundamental principles. However, classical methods were developed to analyze particular types of structures, whereas matrix methods are more general and systematic so that they can be conveniently programmed on computers. Two different methods can be used for matrix analysis of structures, namely the flexibility and stiffness methods. The stiffness method is more systematic and can be implemented more easily on computers and is therefore currently preferred in professional practice. Frame structures are composed of straight members whose lengths are significantly larger than their cross-sectional dimensions. Frame structures can be classified into six basic categories such as plain trusses, beams, plain frames, space trusses, grids, and space frames. An analytical model is a simplified or idealized representation of a real structure for the purpose of analysis. Frame structures are modeled as assemblages of straight members connected at their ends to joints, and these analytical models are represented by line diagrams. The analysis of structures involves three fundamental relationships. First, we have the equilibrium equations, compatibility conditions, and constitutive relations. The principle of virtual work for deformable bodies states that if a deformable structure, which is in equilibrium, is subjected to a small compatible virtual displacement, then the virtual external work is equal to the virtual strain energy stored in the structure. Linear structural analysis is based on two fundamental assumptions. First, we have the stress-strain relationship for the structural material is linearly elastic, and the structure's deformations are so small that the equilibrium equations can be based on the undeformed geometry of the structure.